In this video I talk about Gaussian mixture models and how they can be used for clustering data. The video is based on my example script example_Gauss_mix. We start as usual in the preamble. I define some colors for the components of the mixture. Now, what is a Gaussian mixture? Well, it's easily defined via its PDF, its probability density function. The PDF of a Gaussian mixture is nothing but a weighted sum of univariate or multivariate normal PDFs. The mixture must be properly normalized to 1, so this means that the weights must be non-negative and sum to 1. Let me illustrate the concept by a mixture with 3 bivariate normal components. First step, we define the mean vectors. We have to have a row in the matrix mu for each component. This means that the first row is the mean vector of the first bivariate component. The second row is the mean vector of the second bivariate component, and the third row is the mean vector of the third bivariate component. Next, we have to define a 3D array. I call it capital sigma. It has to be 3D. The last index indicates the component, and the first 2 indices indicate the covariance matrix. Since we are dealing with bivariate components, the indices 1 and 2 have to run from 1 to 2. And this contains the covariance matrix, which is on the right-hand side of the first component. So sigma looks like this. Well, let's better put it like this. So this is the first page of the array, as it's called in Matlab, and the content of this page is this covariance matrix. Likewise for the second and the third component, so we can see the covariance matrix of the first component, of the second component, and of the third component in this display. Finally, we have to define the component proportions. As I said, they must sum to 1, so this assertment checks that it actually sums to 1. Now we are ready to generate an object of class GM distribution, a Gaussian mixture distribution. Let's check the class, it's GM distribution. Let's check the field names. The fields contain, among others, the component proportions, the means, the covariance matrices, and some other information like the number of components, and so on. Now we are ready to make a surface plot of the PDF, which is a function of 2 variables. I will plot the PDF in the rectangle defined by the limits in x and y. We produce the mesh grid in the usual way, and we can plot the PDF. Let's have a closer look at the PDF. Let's rotate it, for instance. You see that in this case the PDF has only 2 peaks, although it has 3 components. The reason is that 2 of the components have a large overlap, so that there is only a single peak for the components. We can try to choose different mean values and then we can get 3 peaks. But let's first plot the contour lines. So let's rotate that back in the usual view. Now let's plot the contour lines. So I skip the computation until line 58. And here we get the contour lines. You remember that the contour lines of a normal distribution are elliptic, they are ellipses. This is of course no longer the case with a Gaussian mixture. The contour lines can be arbitrarily complex. In this case, we clearly see the 2 peaks. Now let's try to see 3 peaks. This is not very difficult. We just have to move the mean value of the second component a bit further away from the first component. So let's now repeat the graphical representation. We don't need this breakpoint anymore. Okay, now we see actually 3 peaks in the rotated view. And you see that you can generate a large number of shapes by using Gaussian mixtures with a sufficient number of components. See, these are the contour lines. It's no longer possible to easily compute the probability content of a contour line. This involves very complicated integrals and can certainly not be done analytically. Now I want to continue with the application of Gaussian mixture models to clustering of data. In this case, I use univariate mixtures in order to get a simple graphical representation. I start with clearing the matrix mu and the 3D array sigma. I set an interval from -15 to 15, which will be used for the graphical representation. And I will use 3 different examples with 2, 3, or 4 univariate components. Let's start with 2 components. The matrix mu now has 2 rows because we have 2 components, but each row is only a single number, so mu is effectively a vector. The vector sigma, sig, contains the standard deviations, and the vector prop contains the proportions. Let me note this here. These are the mean values, and these are the standard deviations. We assert that the proportions sum to 1. We set a figure. And now we plot the component PDFs times their proportion, so that their sum is exactly the PDF of the mixture. Okay, so we now see the component PDFs times their proportion. So these, they are normalized to their proportion, not to 1. We have a narrow component centered around 0 and a wide component also centered around 0. This is, by the way, a very useful model to describe measurement or observations errors with outliers. So the core, the narrow part, describes the normal observations, so to speak, and the wide component describes the outliers. Now we have to create a 3D array capital sigma, and let me recall that the third index indicates the component, and for each component we now do not have a matrix but just a variance. So we can define or create the 3D array sigma in this way. Let's have a look at sigma again. So we have two components. So the index 3 runs from 1 to 2. So page 1 describes component 1, page 2 describes component 2. And on each page we have just a variance, not a standard deviation, but a variance. So the first page is 1 and the second page is 16, which is 4 squared. Now we can create the distribution object and we can plot the PDF of the mixture by using the method PDF in line 93, the method PDF of this object. So let me finish on the plot. Here we are. So blue is PDF of component 1, normalized to its proportion. Magenta is PDF of component 2, normalized to its proportion. And red, the thick red line, is the PDF of the mixture, which is then properly normalized to 1. Next, I want to show you how to fit Gaussian mixtures to data and then to use the fitted mixture to find clusters in the data. Let's first simulate data from the Gaussian mixture we have just created. This can be done via the method random of this object. N tot is a total number of simulated data, and R are the random numbers, and lab are the labels. They indicate from which component these random numbers were generated. Please note that the clustering, which we are now going to do, is unsupervised, which means we do not use the information in the labels. Just to make it more general, I introduce a random permutation. This is not really necessary. So what do the labels look like? Well, they are just integers from 1 to 2. We have two components. And let's have a look at the first random number and its label. So the observation minus 3.6686 was generated from component 2, which is the white component in the mixture. Let's show what the data look like via a histogram. So these are the data. You can see that the tails are too fat for a single normal distribution, so it makes sense to fit a Gaussian mixture with two components to these data. By the way, finding the correct number of components is a highly non-trivial problem, which I cannot address in this video. So I will just use the correct number of components for the fits. The fit is done by the method fit gmdist applied to the data vector R and with the information how many components should be fitted. You can of course try to fit with 3 or a single component, but here we are going to use the correct number, the true number of components for the sake of simplicity. So gmfit is also of the class gm distribution. We have the same field names, the same methods as before. Now let's plot the PDF of the fitted mixture, which is the method PDF of the object gmfit. So you see that the fitted mixture PDF describes the histogram quite well, especially the tails, which are much too fat for a single normal distribution. Let's extract the component proportions from the fitted mixture. I recall that the true proportions were 0.45 and 0.55. Let's have a look at the estimated components means. So they are minus 0.08 and minus 0.11 for first component, and the covariance matrices of the components are in VFit. Remember, these are variances, and if we take the square root, we get the standard deviations. The true values were 1 and 4. You can remember, you can observe a very important effect here. The order of the components in the fitted mixture is not necessarily the same as in the definition that was used in generating the observations. For instance, in this mixture we have defined here with 2 components, the standard deviation of the first component was 1 and the standard deviation of the second component was 4. It seems that in the fitted mixture the 2 components are switched. Of course, the fit cannot know the order of the components in our definition. The fit sees only the observations and not the true labels. If the order of the components is different from the true order, this is called label switching. And we'll see in a minute how to correct for the label switching if you want to analyze the performance of the clustering. Let's now plot also the component PDFs normalized to their proportion. So here we see, again in blue, the PDF of fitted component 1. This used to be component 2 in the definition. So we have label switching. In magenta, PDF of fitted component 2. This used to be component 1 in the definition. The PDF of the fitted mixture in red, thick line in red, and in black, the PDF of the true mixture. You see that the red and the black line are very similar, so this indicates that we found a good fit of the data to this particular mixture model. Now we want to associate the observations to the components of the mixture. This is done in the following way. Take an observation, let's say, take an observation at x equals 5 in figure 21. You see that the probability under component 1 is very small, because component 1, the magenta curve, is almost 0 at 5. In contrast, the PDF of the blue component is quite large compared to the PDF of the magenta component. So this observation will be associated with the blue component, which has number 1 here and had number 2 in the original definition. So by comparing the values of the component PDFs, one can associate each observation to a certain component. And this is done by the function, the method cluster. So with an object gmfit, we invoke the method cluster. We give the observations to this method and we get back the association. This vector is now a vector of labels that indicates to which component each observation was associated. Let's now plot or histogram the observations with the respective color of their cluster. Let me also draw the legend again. So the data associated to component 1, which was a blue component, they are mainly in the tails. In contrast, the data associated to component 2, which was the magenta component, the central component, these data are associated to component 2. And there is of course some overlap. For instance, in the bin at -2, part of the components is associated to cluster component 1 and other ones are associated to component 2. Now we want to analyze the clustering and find out how many associations are correct and how many are wrong. To this end, we have to correct the label switching. Otherwise, we get the wrong basis of comparison. We have to find out which components in the fitted mixture correspond to which components in the original definition, which is coded in the vector lab in 102. So lab contains the labels for the true association, and ASSOC, the vector ASSOC, contains the labels for the found association. But a comparison makes sense only after we correct for the label switching. Now this can be done in various ways. If the number of components is not too large, we can in fact try all permutations, all possible permutations of the labels. There are just two here. There are just two permutations. So in this case, this is very simple. So I loop over all permutations of the numbers 1 and 2. These are just 2, 1 and 1, 2. And I compare the fitted mean values and the fitted sigmas with the true mean values and the true sigmas. This comparison is done by computing, for instance, by computing the norm of this vector. So let me show what this vector looks like for this permutation. So these are the differences between the mean values and the sigmas for permutation 2, 1. So for an interchange of component 1 and 2. The norm of this vector is about 0.23. And I remember the smallest value of d. Now we have the permutation 1, 2. Let's have again a look at this vector, and you see that the norm is much larger than before. The norm is now larger than 4. So obviously the first permutation in this array, the switch between 1 and 2, gives the best match between sigmas and mean values. Now I can correct the association by switching according to the permutation in the vector IP min. So ASCOR contains now the found associations but corrected for the label switching. Now I show you an interesting object, a 2D histogram. I make a histogram of the correct labels versus the corrected associations that have been found by the clustering. So let's have a slightly different look. Okay, so where are the correct clusterings? Well, the correct clusterings are those where the true label, the vector lab, and the corrected association, the found labels, are identical. So the correct associations are the sum of the frequency of the bin where both lab and ASCOR are 1, and the bin where both ASCOR and lab are 2. So this is a slightly different view, and the correct associations are in the diagonal of this 2D histogram, which we used to call a Lego plot in physics. Okay, we can also now plot simply the values of this histogram, and this is called a confusion matrix. I call it capital CM for confusion matrix. And this matrix shows the number and the type of the wrong associations. The first row of this matrix corresponds to label equals 1, and we see we have found 554 correct associations for this label and 38 wrong associations. The second row is for the true label 2, and we found 237 correct associations for this value of the label and 171 wrong associations. So the matrix need not be symmetric. We can now compute the number of correct component associations by summing over the diagonal and dividing by the total number, which is 1000. So we have 79% correct associations, and the rest are wrong associations, about 21%. Now let's repeat this with another mixture, in this case with 3 components.